So the first two equations, basically, they are linked with the electromechanical motion, or the mechanical motion, you can say. Electromechanical motion. In short, that actually those two equations represents the acceleration of the rotor body. And the third one is actually, after much simplification, we should say, after much simplification of our original 2.2 model. Okay, remember 2.2, we had one d-axis coil, one field coil along the d-axis, and one q-axis coil, and the second q-axis coil. These two were the damper coils along the q-axis. So in total, we had 4 coils, 2 along the d-axis and 2 along the q-axis. So we called it 2.2 model. But however, we neglected the effects of the damper coils for simplification. So we got rid of these 1D dynamics, we got rid of this 1Q as well as the 2Q dynamics, and we were ultimately left with this flux decay in the field circuit. So the flux decay dynamics is represented by the third equation, which is actually the related to the electrical circuit, okay, electrical dynamics. So the first two are electromechanical motion or electromechanical dynamics, and the third one is the purely electrical dynamics. And in summary, this model, this third order model, in the literature, it is also termed as the flux decay model. The flux decay model. So once we have this model, now we will continue with the discussion of this model. So our target would be to analyze some phenomena occurring within the machine or within the power system where we expect to have a synchronous machine, of course, as a generating source. And then we expect that this synchronous machine is, of course, delivering some power to a network, let's say a network, a transmission network, and ultimately we have a very large network, which we call, hypothetically, we model it like an infinite bus. So the synchronous machine that we model till now is basically, these three equations are basically representing simply this machine over here, the generating source. And then we also have to think about, well, the transmission line, and we also have to think about this infinite bus so that we can complete our model. And then only we can try to solve or try to analyze some, let's say, stability phenomena, be it the rotor stability, rotor angle stability, or the voltage stability, or any other frequency stability, and so on. However, the modeling associated with different sorts of stability, like rotor angle stability or other two types, the modeling itself varies a lot. So the model that we are focusing on is basically, we will be looking for the small disturbance model. So we'll be looking to analyze this small disturbance dynamics. And we'll be looking at the rotor angle stability. So this will be our target for the time being. Okay, so we'll be looking at small disturbance dynamics, or in short, we can even call it small disturbance rotor angle stability. Okay, if we combine these two concepts, small disturbance and rotor angle, so combinedly, we will be trying to analyze this thing, small disturbance rotor angle stability. For which system? For, let's say, a system of this form. We will call it a single machine infinite bus system, SMIB. In short, if we expand this form, that is single machine infinite bus system. That means we have a single machine which is delivering power using, of course, a transmission network through to an infinite bus, which is basically an equivalent of a very large network, comprising of many generators and many other equipments present in a real power system. So till now, what we have obtained, so we have to reach ultimately there. Okay, this is our target, to analyze the small disturbance dynamics or small disturbance stability with respect to the rotor dynamics. To reach there, we still have to work a little bit more. Okay, so let's try to start from there, and let's try, we will reach there ultimately. This is our target initially. So before we try to reach there, let's see where we are actually. So what we have got till now is the simplified third order model, or the flux decay model, where we have three ordinary differential equations, okay, with respect to time. Three ordinary differential equations with respect to time. So in short, we can also call it systems of ODE, systems of ODE, okay, ordinary differential equation, systems of ODE. So now, can anyone tell how can we approach for the solution to this problem of a system of ODE? So what I'm talking about is this. So in short, these three equations gives us this systems of ODE. ODE stands for ordinary differential equation, because you can easily see that the derivative term is like d delta over dt. There is no di delta over something. Okay, so it's not a di operator, it's not partial operator, it's not PDE, rather it is ODE. So this sort of equation, how do you solve it? Any idea? And what is meant by solving this actually? When I say, well, I want to solve these three equations all together, because these three combinedly represents a system, a single machine over here, synchronous machine, synchronous generator specifically. So we have got a systems of ODE. Now we want to solve it. By solving, I mean, I am looking for these three things. Explicitly, I'm looking for delta versus time. So the equation itself says it is in differential form with respect to time for the rotor angle. So when I say I'm looking for the solution, what I mean is this: I'm looking for this delta versus t plot. So these are the plots I'm looking for. Then I'm also looking for omega versus time, because this is the second equation. The second equation is d omega over dt. The single dot over omega is actually representing the d by dt operator, differential operator with respect to time. So I'm also looking for the second plot, omega versus t. So what should be the third one? What should be the third plot? Out of the third equation, what should we try to obtain? Or what would be the solution? So this equation is simply dEq prime over dt. So when I say I'm looking for the solution, actually I'm looking for this EQ dash versus t. So while we will be solving this, actually we'll be looking at specifically these three plots, these three graphs or plots, time domain plots. Now, how to achieve these three? Any idea from your undergrad level knowledge? How do you solve a system of ODE? Have you done anything like this? Y double dash plus 5y dash plus 2y equals to 5. Do you remember something like this in any of your math course?
Yes, sir.
What was that? What are these?
This is, sir, actually that was square type, y square plus 5y plus this type.
Yeah, actually, when you take the Laplace, then it will become that what you are looking, what you are trying to say. But before that, what are these actually? These two. This y double dash means what? It is basically nothing but a second order.
A double derivative.
Double derivative. This is now you are trying to say something. That's good. You should say something. Otherwise, I feel alone in the class. Okay. So this is 2i's y is equals to 5. So basically this double dash is simply d square y over dt squared. The single dash over y is, it means it is d over dt for y. And then you have twice y. There is no derivative term. So it is simply the algebraic term. And this is the forcing function 5. Now, do you remember how did you solve that? Anyone? Well, so this is nothing but a second order ODE, right?
Yes, sir. This is
Nothing
second
but a
order.
second order ODE. So at least you remember that you came up with these things in your undergrad level, right?
Yes, sir.
Second order ODE. But we are not in the undergrad level. So, but even we can take help of the undergrad knowledge. So what we can do one way,
Excuse me, sir.
yeah.
Perhaps your sound is very low. Is it only my problem or everybody suffering?
Is it okay now?
Yes, sir. Yeah. Now this is okay. Please.
Okay, okay. So thanks for informing me. Okay, so so this is the second order ODE, and one way to solve these is to take help. You can do it, let's say in general, in two different ways. One is the analytical way, which probably most of us were taught in our undergrad level. When we try to solve this, we came up with some complementary solution, particular integral. Remember these terms? Complementary function and particular integral, something like that. And we then applied superposition theorem to combine those two. So one was YC, another one was YP. Remember? Probably or probably not, doesn't matter. Because in this course, we are not going for the analytical solution. We will be applying some numerical technique. Now, any of you had any courses before on numerical technique? Of course, some of you might.
Numerical analysis technique.
Yeah, numerical analysis technique. So can you list some of the names?
Newton-Raphson.
Excellent. Newton-Raphson is one of the method. Gauss's method or Gauss-Seidel method. Then the Euler's method, modified Euler's method, okay, or predictor character method, or Ranga-Gupta method. There are many. So probably we can use the simplest one. Let's say the Euler method. Okay, we will use it at some point of our course. Okay, but probably not today. But I'm just saying what we are actually trying to do ultimately. So what we will do, we will be using some numerical technique, be it the simplest one or the most complex one, whatever we adopt. Ultimately, those techniques will help us to reach here, right? To get these three. So we can easily solve them. We apply the Euler method, or the Euler method, whatever you say. And then we are looking for these delta versus time, omega versus time, and EQ dash versus time. So that means by using the Euler method or any numerical method, we can solve them. So before we go there, we have to again go through some or few more steps. So let us see what are those steps. So now the model that we are discussing, as we are saying, this is the third order model. Actually, only these three equations is not sufficient to represent the complete model. If you remember, we besides these three equations, we also had few more equations, okay, along with these three. Now let us see, among all those equations, there are many equations actually. So we have to pick only the necessary ones, okay? Whichever are necessary to complete this model, we will only pick those. So now let us see how we are going to pick those necessary equations to complete our model, the third order model. So this third order, only whatever we are seeing now, these are only representing the dynamic part of the model, okay? The dynamic part of the model. Now, before I proceed, let me ask you another thing. Any of you are familiar with this term, state space model? Anyone in control course or any other course? I don't, linear system analysis, state space approach. No one? That's interesting. So in short, what is the state space model? It's a space, okay, it's a space, of course, where the state variables will lie, okay? So what are the state variables? Let me explain in short. let's say in a very short short manner, in very precise manner, on a brief manner. Have you studied the AC circuit transient analysis? Electrical AC circuit having, let's say, R, L, and C. Okay. So have you studied this transient, switching transient for this in any of your course with, of course, an AC source? So this is series RLC network where you have a switch. This is your, yeah. Have you studied this? Don't say
Yes.
no. Yes, you must have.
Yes.
Yes. So let us try to establish the steady space model for this model, for this network. Okay. Then we will be, I think we will be clear what we are actually trying to mean by steady space model, because if we don't understand the steady space model, then it would be difficult for me to proceed from here. So let's try to proceed from here. So before I close the switch S, okay, before I close the switch S, I assume that there are no energy stored in L or in C. Okay, so they are uncharged. L is uncharged as well as C is uncharged. And before the switch was closed, there was no current flowing. So when we close the switch, before we close the switch, the current was 0, right? Because the circuit was open. When we close the switch, what will happen? There will be a current flow, isn't it? Because the circuit is closed. So that will give you the switching transient for this network. Now, once the switch is closed, we have got a loop. We have got a closed loop. Now, can you apply KVL here? If we apply KVL, what would we get out of this? Anyone?
Yes, sir.
Yes, please. So V in is my source voltage. Then
I will multiply just using current of the ILC element.
I multiplied by R. Then
L di
yeah. So L
di
by dt. Excellent. Why we are taking this form? Why not simply J XL into I? Because we are looking at the transient state. Remember, we are looking at the switching transient. So the current hasn't reached its steady state yet. Current hasn't reached its steady state yet. So across the inductor, the current, there will be some d by dt of the current, okay, because current cannot instantaneously change across or through the inductor. So that's why this will be L di over dt. Whatever through the resistance, it can flow. There is no opposition such as the opposition provided by the L for R. So that's why we can write it down simply as IR. Then what do we write for the C? Let's say we write it as the voltage, capacitor voltage. Okay, we can write it. The capacitor voltage is VC. Now what we do, we can try and make it look like something like this. So if we want to look this equation, if we try to match this equation to look something like this on the left hand side, what should we keep? Here on the left hand side, what do we have? We have d delta over dt, right? So here, what should we keep on the left hand side?
di by dt.
We should keep di over dt. Excellent. So let's keep the L for the time being. We will switch it later on. So if this is the case, then we have minus IR minus VC plus V in, right? And then we simply take this L and we bring it as the denominator for all these three. So that's it. So now we can say, well, now we have successfully made the left hand side look similar to the left hand side here, right? So we have also a coefficient of 1 here, like over here there is a coefficient 1, we can say delta dot. So we can also say this is I dot with a coefficient 1. So we have got a similar representation for the RLC circuit. Now, any other dynamics can you think of for this network, for any of the other elements? This will capture this equation over here. This will capture the current dynamics through the inductor. So my question is, will there be any dynamics across the C or not?
Yes.
So how can we represent that dynamics if it is yes? Can you help?
Integral. You can write
Okay,
it in integral form.
I take your answer, but okay, our target would be to try to mimic this model. Okay, try to make a similar model like this. So you see, there are no integral term. Everything is in differential form. So your answer is okay, but try to make it in differential form. So if following your answer, if I try to make it in differential form, probably I will write it like this, isn't it?
Yes, sir.
So C multiplied by the dynamics of the capacitor across that C. So C dV by dt is equal to the current through the capacitor, isn't it? Of course, you can take it in the integral form by integrating on both sides. Okay, that's your freedom. You have the freedom. But we want this model. We want this equation or dynamic of this RLC circuit. We want it to be identical or the similar looking like this one over here. So that's why we are keeping it in the differential form. We want ODEs. We don't want the integral form. That's why. So now again, we want this dVC over dt to be having only a coefficient of 1. So that's why what we do, we simply erase this C from here and we bring it to the other side like this. Okay. So now, any other dynamics that come to your mind other than these two? Probably not. Okay, if the answer is no, then we have already got the model that we are looking for, and that is the steady space model for this RLC network under the switching transient. So what is the steady space model? In general, the steady space model will look something like this. I'm writing it in general. Later on, I will try to make it look like this. Okay. So first of all, I will take the in general form of the steady space model, and then I will try to say how it looks similar to the model that I'm writing in general. So we have some X vector with, so the bar, over bar is the representation of the vector with a dot. So this dot means it is d over dt. Okay. So we have a capital X bar dot equals a function, some nonlinear function. So in general, this is a nonlinear function, some function of x, comma, some function of u. So that means you, in the steady space model, you have some variables x, which are represented in the differential form, of course, in the first order ODE form, So in the steady space model, you don't see anything like d square or d cube, something like that. Even if you have any model in that form, you have to convert it into this first order ODE form. Of course, in any control course, you have done it. Okay, if you have any higher order, higher dimensional ODE, then you know how to bring it to a lower order dynamics. I hope you have done it already. So this x variable is our state variable. Remember the names or remember the terms. So this is our state variable vector x. Okay, the x over bar is the state variable vector. Then, so on the left hand side, you expect some differential form of the state variable vector. Okay, differential form. The dimension of x can be, the dimension of this is n by 1. Okay, where n is the number of elements inside your vector x. N is the number of elements present in your vector x. So x is n by 1. Similarly, this x bar is also the same variables which we had on the left hand side, but on the right hand side, we don't have any dot. Okay, So on the right hand side, we simply have x. So in the left hand side, there will be differential form. On the right hand side, there won't be any differential form, okay, in the state space model. And what is u? U is the forcing function or the input variable. And it could be m by 1, okay, m number of inputs. So that means your state space model, this is the state space model, okay. So the space that will be spanned by these equations is known as the state space, okay. Or in other words, the state variable vectors, the space spanned by these state space vector variables, or the elements of the state space vector, are known as the, or is known as the state space. And the corresponding dynamic model is known as the state space model. Along with this equation, we also have to write down the output equation. So if I write the output equation, then I should write it in this form. So y, it's another vector, but this is in algebraic form. So the output equation of the state space model is in algebraic form, but the state vector is in differential form. The state vector is in differential form. The output vector is in algebraic form. And you can write it as, let's say, h of x comma u. So that means it could be some other function known as h. And again, that h is function of your state variable vector capital X bar and input to your system. So combinedly these two, this x dot equals f of xu, function of xu, and y equals h of xu, these two gives you the state space model. Any question? If you have any question, please ask. So this is your state space model. No question. Okay, so let me proceed. So whatever I have told, this is in general. In general, the function f and the function h, these are non-linear in nature. So in general, f and h are non-linear in nature. Okay, and a special form of this is the linear form, of course. Okay, special case for the non-linear case is the either you may linearize the non-linear original non-linear model, or you may have a linear model on its own from the very beginning. Okay, so if it is a linear model, if it is a linear form, in the linear form, the same system, that is the state space model, can be represented with the help of matrices in this way. So then you have ax, x dot equals ax plus bu, and y, the output equation, the output vector y is cx plus du, where a, b, c, d are constant matrices of different dimensions. Okay, the dimensions of a, b, c, and d should be such that these multiplications over here, multiplication and addition, are possible. Okay, so accordingly you can find what should be the dimensions of a, b, c, and d. So this is the linear counterpart of the general or the generalized state space model. This is linear state space model. Okay, where again x is the state vector, u is the input vector, y is the output vector. So now, after discussing these basics related to the state variable representation for the systems of ODE or for any dynamic system, now let us focus on this part of RLC switching transient. So what is happening here? We have got this block over here already available to us. Now, can you say in this two equations, what is the dimension of X and which are the elements in X, capital X? Anyone? If you can tell, that means you have understood whatever I have said till now.
IT.
I? We have
I.
I. Okay, excellent. So one of the element we inside the X should be I. Okay, I take your
And
answer.
VC.
I and VC. So excellent. Thank you very much. So my X vector over here is simply, if I write it, I don't have much space. So X vector for this is simply I and VC, and just put a transpose just to make sure that this is a column column vector. Okay, so I and VC. So X is done. What about U? Look at the practical network. What is the U here? How many U are here?
So begin.
V in is the U, although in is a little separated here. In should be subscript to this V. So let me fix it. So in is here, somewhere here. V in is our input. Excellent. So U is the V in. So we have got U, we have got X. What about Y? Remember, we have to also fix a Y. Yes.
IR.
Okay. Actually, Y depends on the designer's choice. Okay. Y depends on the designer's choice. By design, I mean, let's say you are trying to control some of the variables or some of the quantities inside this network. It could be the voltage across the register, or you might want to just record the value. Okay, whichever value you want to record out of this network, you can choose it as your Y. So
Is it voltage across register and interrupt?
it's up to you. You can choose 2, you can choose 3, you can choose all the voltages I want to sense. Okay, I want to measure all of these 3 voltages. In that case, your Y should be something like this. Let me write over there, clear this space. So your Y vector should be what? It would have 3 elements. The first element, as you said, it is VR, the voltage across the register. So I can say V sub R, then
EL.
V sub L, and V sub C. Okay, no problem. Up to this point, there is no problem.
Since already we have take DC in X vector.
Yes. Okay. So it's fine, no problem with this. But the problem will start to appear once you try to represent this equation, let's say in this form. Remember, your Y should be a function of only X and U. Okay, only X and U, if it is in nonlinear form. Again, if it is in linear form, even then the Y should be represented in this manner. So while you pick Y, you have to make sure that, well, you can manipulate your Y elements, Y1, Y2, and Y3 in some manner. After some manipulation, even then you can come up with this pattern of representation for the Y variables. So now let us see, can we do that? Can we do that? So this is a transpose. So what are our elements in X? Okay, we have X and U. So the elements in X are I and VC. Okay, so these are our I and VC. These are our X. So I have to make sure that I can represent my Y with the help of these 2, and plus of course U. There could be some U also here, as mentioned here. So first question, can I represent VR as a function of I and VC or some constant? Yeah, I can. So VR is simply I into R, right?
Yes, sir.
So if the value of R is known, let's say 5 ohms, then it's done. We are done. The first Y1 is done. Next VL, What about VL? It's not straightforward, right? I mean, you might require some manipulation, but at the first glance, it seems that, well, VL is some function of, it's some differential form, but differential form is not allowed, right? Differential form as an element of y is not allowed. So let's drop it for the time being. We don't want to go into the detail here, but it might be possible. It might be possible by some manipulations, but we don't want to go there. Okay, we keep only 2, no problem.
So if you know the value of reactance, we can.
Yeah, even then, VL, remember, it is a dynamic quantity. You can know L, no problem. You can have the value of L, you can have the value of R, no problem. Of course, you will have it. But your di over dt, this is in differential form. That is the problem. In your y, you can't keep any differential form. You see? It's simply h. It is algebraic form. It is not y dot. It is not y dot. So y have to be, the y's have to be in algebraic form. Remember. So for the time being, we stay with the simpler ones. Probably we are not going to use it here. Okay, just I'm showing you how to deal with the y variables. VC, what about VC? VC itself is our second state, right? So we simply can keep VC, no problem. That means once we get the solution of VC, after solving these 2 equations, once we get the solution of VC, then we can say, well, that is our second output. So we can say, well, easily we can track the value of I, we can track the value of VC, and if you want, well, let me help you out. If you want, instead of VL, we can take simply I as our third output variable. Why? Because it's easier to measure it. You know, simply if you place an ammeter here, okay, you can simply measure it, right? We can simply measure it. Or any device which can capture the dynamics even, you can measure it. It's easier compared to thinking about how I'm going to get di over dt. No need to think about it. As I said, it is up to the designer. So you choose your I as your output variable if required, and you take any measuring device and you get the I, and then you calculate di over dt if required. Of course, di over dt can be easily calculated from this equation. If you know everything on the right hand side, then you can get the left hand side expression, but you cannot keep any differential form of variable inside your y. Remember this. So there is the problem. That's why we are unable to keep it inside this vector directly. But instead of that, we can simply measure I, because I is our one of the state variables. So we can keep I. So in this way, we can deal with this.
Can we skip I?
I said it's up to you. You can skip I, no problem. You can skip VR. You can only keep VC. You can only keep I. It depends on your target. Get it? It depends on your target. What is your target? Let's say you are trying to control, let's say if it is a DC motor, okay? If it is a DC motor, let's say. So I'm going too far probably, but I have to explain this thing. Otherwise, probably it might cause confusion in your mind. So let's say if you have a DC motor, shunt motor, so the field circuit would be attached here, and you have to apply some voltage, of course, DC voltage. Okay. So the same voltage that would feed the field circuit, that voltage would also feed the armature circuit. That's why it is self-excited, or this is shunt connected DC motor. Now, what is your target out of the DC motor? Of course, there should be some load, right? There should be some load, let's say L, load, L-O-A-D, load. And of course, there will be some rotation, speed, okay? So now let's say let's say you want to have the steady space model for this DC machine. Of course, you can go for it. This model is also available in any control course. You can also find it, the dynamic model, and you can take it and you can convert it into your required steady space form, no problem. But coming to the question of choosing the Y value, okay, this is the problem here. So now let's say, what do you want to measure, or what do you want to choose as your output variable for this system? Do you want to measure the torque, or do you want to measure the speed, or do you want to measure the corresponding output power for the motor, or what? Are you getting my point?
Yes, sir. Yes, sir.
So depending on your choice, let's say your target is only to look at the torque. So just keep the torque as your Y variable. No need to calculate N. No need to attach a tachometer with that. Just set a torque meter or dynamometer that would give you the value of the torque. On the other hand, if your target is to control the speed, no need to look at the torque. Just keep the speed, keep a tachometer, keep track of the N value, and include it as the variable in your Y vector. If you want both, okay, take both, no problem. So it's up to you. You get it now?
Yes, sir.
So it is up to your choice, or up to your target, what you want to do actually ultimately with this dynamic system. Depending on that, you choose your Y, no problem. Okay, so now let's proceed. So we have discussed about the nonlinear steady space model, the linear steady space model. Now, how can we get the steady space model for our RLC system? Let us see. How can we get the ABCD matrix out of these two equations? Because these are the ultimate two equations. So the so the required equations would be something like this. So my first equation is, probably I will need some more space. So it is this. Okay. So the first equation would be di over dt. This is my x1 dot. If we take I as my x1 element inside the x vector. So this is my x vector. So this is x1. And you can say this is small x1 and small x2 inside my x vector, steady space vector. The second element is dvc over dt. Remember, I am now formulating my ABCD matrix for RLC network. Why I'm directly going to the ABCD matrix? Because actually I know beforehand that this is a linear model. Okay, this is a linear model. That's why I'm directly going for the linearized representation of the steady space model. Okay. There will be some entries. So what was the equation? Remember, x dot equals ax
Bar.
plus, yeah, bu. Yes. Anything you want to ask?
AX bar.
Okay, bar, I'm dropping it because we know there are bars. It will kill some time, nothing else. There are bars, okay? X bar dot equals ax bar plus bu bar. Bar is the representation of the vector, but I'm dropping it for the next few, probably for the next few, next part of the discussion. I'm going to drop it. Okay, I'm not going to use it every time. But we know that this x means that this is a vector. There are several elements inside it. We know there are two elements, so that's it. Inside x, this is ax. So this is the x. This is my x bar. This is my x bar dot. So here I will have my x. So ax plus bu. This is my b. And then I will have u. What is my u? U is simply v in. So I can directly write it v in for my RLC network. So here inside I will have my b. So now can you fill up the blank spaces for a and b? Let's start with the first one, di over dt. So let's only go through the coefficients. So what would be the first one here? What is the relation of di by dt and I?
Minus R.
Minus I over R. Excellent. Minus I over R. What about the second one? This should be VC.
BC, yes. BC.
So
Minus
is
1 over L.
minus 1 upon L. Good. Then anything else? We have some class over here for the B matrix. Anything as a function of V in? Yes, we have 1 upon L. You get it? Very easy. Now come to the second one, dVc over dt. Any function, anything as a function of I? Yes, we have a function of I, that is 1 upon C. That's the first one. Second one, any function, anything is a function of Vc?
No, sir.
0.
No. Anything as a function of V in? No.
0.
So that's it. So this is your state space model in linearized form. Okay. Now you get the idea how to develop the state space model. Simply you have to use the very basic rules that you know. If it is a mechanical system, apply the corresponding laws which are related to that system. If it is an electrical system, of course, there will be R, L, and C in the equivalent network. So simply use KCL, KVL, or simply try to solve that network. If it is a very complex network, try to apply any simplifying concept or simplifying technique, which will simplify the model, and then you can simply apply KCL and KVL. Very basic things. And that will give you some differential equations. So what about y? Y already I have mentioned, okay? We took a bit of time for discussing y. So y depends upon you. Let's say if I take y equals Vc, if I take y equals Vc only, then what should be my y equals Cx plus du? Yes, what should be my C? First, let me write the state variable ones, vectors. So I and Vc is my X. So this should be my C plus some D multiplied by V in. Okay, now can you fill up the blank spaces? What is this? Y equals Vc. So is my output any function of I? No. Is it a function of Vc? Yes, it is simply Vc. So simply 1. Is my output any function of input? No. So simply 0. So this is my D and that is my C. You get it now, the idea? And depending on if you choose any other vectors, or sorry, any other elements inside your Y vector, that is the output vector, then of course the dimension and the entries will be changed here for C and maybe for D also, for any other network. So that is the summary for the state space model. Now, with this summary, let us again go or come back to our world. That was the world of synchronous machine. So now let's continue with this synchronous machine model discussion in light of the state space model. So if I want to say that, well, I want to express, or I want to say that, well, these three equations are or is my state space model. Let us see whether I can transform these three, or whether I can say whether my claim is correct or not, that these three are sufficient to give me the state space model. So at the first look, you should be able to identify now what should be your vector X. Can anyone tell what should be the vector X over here? The state space vector for these three equations. What should I write? What is the first?
Omega.
Sorry?
Omega. And delta.
Yeah, we follow
Delta.
sequentially.
Yeah, delta.
Why are you jumping? No problem. Just go slowly. Okay, so delta, yeah, okay. Because delta has a dot term, okay? Probably it is not visible to all, but there is a dot. Delta dot. So delta has a dot, so this is x1 dot. Okay, so delta is our x1. What is the second one? Omega.
Yeah.
Because we have omega dot. What is the third one?
PQ
PQ prime. That's it. So this is your X. So now you see it's very easy now. After that initial discussion, now it looks very easy. So we have got the X vector. Now, if you remember, for our synchronous machine, what should be the input? Can anyone tell? Synchronous generator. Don't talk about machine only. We fix it as a generator. So for a generator, what is the input?
Mechanical power.
Mechanical power. Do you see the presence of mechanical power here anywhere?
Yes. PM, second equation.
Excellent. So PM. So we pick it. Anything else? If you only provide mechanical power and you do not provide any excitation voltage, will it work? Will it give you any voltage output?
No.
So we need some excitation voltage. So what is that? This EFD, if you have forgotten, so let me go back a few slides to help you recall what was EFD. Yeah. So you see EFD here is a function of VFD, right? Whereas the VFD was our original or actual applied voltage. So EFD is a transformed form of the original VFD, input field voltage, field excitation voltage. So because we have the presence of EFD, we don't bother about VFD now for the time being. We have EFD. That is the transformed form of VFD. That is the field excitation voltage. So EFD could be our another input. Is it clear? Because for proper working of your system, of your synchronous generator, you need mechanical rotation as well as you also need the field excitation. So we take two inputs for our system. Any confusion, please ask me, because it is very important. This formulation is very, very important. Understanding of this formulation. So these are your PM and EFD. So we have got X, we have got U. What is left? Y, right? We will not bother too much about Y because it will create chaos. So we leave it to you, okay? You are designer. We have 16, besides me, we have 16 more participants in this session. So it's up to you. You choose it and you form it, whatever you want, okay? I will leave it to you. So it's your designer's choice. You can design accordingly. But you try to pick the Y value in such a way that you don't have to we don't have to deal with any d by dt term. Okay, you don't bring any d by dt term in Y. Y is an algebraic expression, unlike X dot. Okay, now this definition is okay, done. Now the actual problem starts. The actual problem is the definition of the state space model says that X dot should only be the function of the X itself and some U, if some U is there, and Y also is some another function, nonlinear function, of course, some X and some U. So now let's say whether this representation is possible or not in this form, whatever form we have. So let's start from equation number. We have three equations. Okay, so let's start from these three. The equation number, the topmost equation for delta dot. So the delta dot is equals to what? Omega base. What is omega base? What is the physical name of this?
Omega means angular frequency.
Omega means angular frequency. Excellent. What is base?
Is angular frequency, sir.
Base. Remember, we were talking about per unitization of the system. So what do you think? Should the base speed be fixed or a variable?
Fixed, should be fixed.
Fixed. So this is a constant. We don't have to bother about that. Done. Next, omega. What is omega?
Is it variable?
It is a variable, and fortunately, this is one of the state variables. So done. This is our x2. So we name it as x2. If you like, you can name it x1, x2, and x3. Okay. So this is our state variable. So I'm just mentioning it as x2. 1, it is a constant. So the first equation is done. It is already in this form. That means my first equation, if I say it like x1 dot, is of course the function of, we can write it like this. x1 dot is some constant multiplied by omega. What is omega? If this is x1, this should be x2. x2 minus 1. Okay, so x1 dot is a function of some constant and some state variable. So that is done. First one is done. We don't have to bother about it. Come to the second one. Omega dot. What is H?
Constant.
H is a constant. Okay, per unit inertia constant. The unit is in second. So it's a constant. We don't have to bother about it. What is PM? PM is the input. So that is also okay. No problem, because X dot can be a function of U. Okay, some function of U. So U is present there. No problem. Done. We don't have to bother about it. But what is PE? Can you
Electrical
see?
power.
Yeah, electrical power. But can you see anywhere here the presence of P inside this definition of X, U, and Y? Why we leave it, but X and U? Because X dot should be function of X and U. There shouldn't be any other thing.
Sir, Y bar. Y bar is the output.
Okay, Y bar. This is why I'm saying again. Y is not appearing here. You see?
Yes, sir.
Inside X dot, there is no Y, no place of Y. But inside Y, there is place of X. It is one way only. It's not two-way communicate. No, two-way, both ways not. It's not possible. It's only one-way journey. X dot can be a function of X, okay, but not a function of Y. On the other hand, Y can be a function of X. So inside X dot, you don't expect the presence of Y. Yeah, of course, you can take PE, output power, as your Y. No problem. That's very good idea. If you want, you can keep it for the time being. Later on, we will deal with it. No problem. So for the time being, we choose one of the output as our output power. We can, no problem. We will detail our discussion on this. We will make detailed discussion on this later on, because Y creates problem. We will take it later on. But is PE a member of this X? No.
No,
Answer
sir.
is no. Is PE a member of U? No.
No, sir.
So how to deal with this? This is the question. This is where the problem starts. It's not straightforward. Steady space modeling is not always as simple as we did for the RLC network. Okay. So let's see how we can get rid of this PE. So what we have to do, at least we know that what we want. Okay. We are not totally lost. We have some help. The help is what? If we can somehow express this PE as some function of delta omega EQ prime, and if needed, even PM and EFD, right? Then we are done. Do you get this point? This last line that I said? If somehow we can express this PE as some function of X and U, this is our target, right? So what is inside X? Inside X, we have delta, we have omega, we have EQ prime. What is inside U? We have PM and we have EFD. So if somehow we can relate PE with any of these, then we are done, isn't it?
Yes, sir.
Okay. So for the time being, we leave it here, okay, because we have to deal with few other variables. But at least we know that, well, PE itself is not sufficient for representing the model as a steady space model. We have to do something with PE, and that something means we have to express PE as some function of delta omega, this. In short, X and U, X bar and U bar. Now let's continue. What is D? D is the damping coefficient. So it is a constant. So it is a constant. So we don't have to bother about this. This should be available. This should be available. What about omega minus 1? Again, omega is your X2. So don't have to bother about omega 1. It is a constant. So only thing that we need to deal with further is PE. Remember. So PE needs some further PE needs some further attention. So well, now let's take the last one, EQ dash dot. What is TDO dash? TDO dash is named as open circuit. DX is open circuit time constant, and it looks like, let me go back to that slide. It looks like something like this. You see, TDO dash is XFD divided by omega base RFD. So what is XFD? It is the reactance of the field circuit coil. RFD, it is the resistance of the field circuit coil. Omega base, it is the base angular frequency, which is a constant. So TDO dash is some function of some real quantities, okay? Coil inductance in the field circuit and coil resistance in the field circuit. So this is a time constant, and that should be known, because once you design the coil, you expect your inductance and the resistances to be fixed. At the same time, of course, omega base should be a constant once you set your base frequency to a certain value. So TDO dash is a constant. So we don't have to bother about this. This value should be given. Or of course, there are certain standard tests through which you can identify this TDO dash. But once you buy a machine, then this dynamic data set should reflect the presence of TDO dash there. Then what is EFD?
Voltage across field
EFD,
coil.
yeah, EFD for the time being, it is the input, some transformed form of VFD. It is linked with some function of VFD, which is the original or the actual field voltage, DC voltage applied in the field rotor circuit. So that is input. Don't have to bother. This is, you can say U2. This PM is U1. Okay, U1 element, the first element in the vector U, and EFD is the second element in the vector U. EQ dash, what is EQ dash? EQ dash itself is a state variable, so we don't have to bother. This is X3. XD and XD dash, these are reactances. Again, this should be provided by the manufacturer in the dynamic data set, or even if you don't have that data set, if the machine is old, you have lost it, the machine is pretty old, you don't have the data available with you, then of course there are certain standard tests by which you can determine these values, XD and XD dash, for a physical machine, real machine. So these are fixed. Once you know these values, these are fixed. So these are constants. What is ID? Again, another problem. ID, it's not available here, it's not available there. So ID, again, we have to do something with ID, so that ID is some, okay, let me make it F1. So ID is another function of delta, omega, and all these things. Okay. Sorry, EFD. So this is the summary till now. Probably we haven't moved from this slide. We have only covered one slide today, but probably we have covered many things even in one slide. Okay. So the content may look very small, but there are many things inside. So to represent this system, in summary, to represent or to say that this third order system is a state space model, only by writing down these three equations is not sufficient. So we have to pay further attention to our two of the variables which are here. One is the real power output from the synchronous machine. Another one is the d-axis d-axis current component for the generator output current. What is ID? It is nothing but d-axis component of the generator current. So this is the d-axis component, d component of I terminal or generator current, whatever you say, I current, I generator. So now our next target is to look into this, how we are going to have this PE and ID expressed in terms of all these, not all these, not required, not a must. It is not a must to represent in the form of all of these, but at least if some of these are there, then it's done. Even if at least one of them is there, we are done. Because we don't have to pick all the state variables to represent PE. Okay, we don't have to take help from all state variables. Any single state variable and any single input is enough. Or even if there is no input, no problem. Okay, that component might also be 0. But at least either there should be some effect of some X or some effect of some U. Okay, one of the X or one of the U at least should be there. So that is our target next. And for doing that, we will take help of the network that I said, that is the single machine infinite bus network. So probably today we have ran out of time. We don't have enough time to look into this important topic. So what we will do in the next class, this is our network that we will look into, inshallah, on Friday, coming Friday. So you see we have a single machine generator. This is the synchronous generator supplying real power PT and the reactive power QT, and also supplying current IT to its own bus where it is connected directly VT. But of course you can consider some transformer also here, but for simplicity I have neglected the presence of transformer. But of course there should be some transformer before you step up the before you can actually match the voltage of the generator output to the transmission level. Okay, so you, of course, in practice there should be some transformer. Nevertheless, this is the network that we are going to consider further for our analysis, and this XL would be the transmission line reactance. Again, here in the transmission line we are not considering any RL. So as I said in the last class, why we are ignoring all the R's? Because in practice, as a designer, we try to minimize these R as much as possible. Okay, because R is only there to actually give you some losses, real power losses. We don't want the losses. So you try to keep, while we design the transmission network, the cable or the overhead lines, we try to minimize this RL as much as possible. So we can say RL is far, far less than XL. And with this assumption, we can ignore it. So this XL is the inductive reactance of the transmission network through which the power is being transmitted to the large network, which is represented by the infinite bus having a voltage VB. And in the next class, inshallah, we will be looking into the development of the phasor diagram. Of course, before that, we will go through a few calculations, which will help us. Actually, these are some of the calculations. At the end, you will see that, well, PE, of course, here it is not clear. It's not that much clear, but inshallah, in the next class, it will be clear, okay, how we are going to reach to our target.
Sir, this PDF that you're showing things from, is this PDF available in your program?
Yeah, it's available, but it's not yet posted because every time I find 1 or 2 errors here and there. So every time, unless I am finishing this, I'm not going to post it. But if you want, I can share this with you, but it will be edited if there are any errors. Okay.
Okay, sir.
No problem.
You can upload it after finishing the lecture. Hopefully it will be finishing the next class.
No problem. If you want, I can also share it today, because probably I'm done with a few more slides. Probably 3 more slides is there, so I can upload it today. No problem.
Okay, sir.
Okay. Okay. Any other question? Any other question? Anything? Nothing. Okay then. So see you inshallah on next Friday, coming Friday. Okay. Assalamu alaikum.
Walaikum assalam.